Here comes an important concept in NMR spectroscopy called as the coupling constant. The coupling constant is generally denoted by the letter J, and it is the distance between two adjacent peaks of a split NMR signal in Hertz. Let me explain this with an example. Here is 1,1-dichloroethane, and you can see there are two different types of protons, proton A and proton B. Proton A will be split by proton B as a doublet. Why? Because you have only one neighboring hydrogen, so it's going to be 1 plus 1, that's going to be a doublet. And similarly, proton B will be split by proton A as a quadret, because there are three neighboring hydrogens, so it's going to be 3 plus 1, that's going to be equivalent to a quadret. Okay. And in NMR spectrum, you can see that here is your quadret and here is your doublet. Okay. Now, the coupling constant of the A proton split by the B proton is going to be represented as JAB, whereas the coupling constant for the B proton split by the A proton is going to be represented as JBA. Important thing to remember here in NMR spectroscopy is the coupled protons will have the exact same coupling constant. What it means is, if I'm going to measure the distance between these two peaks or measure the distance between these two peaks, they are going to be exactly the same. If this is going to be 8 Hertz, this is also going to be 8 Hertz. Here is the table that gives the coupling constants for different protons, where you can see that the two non-equivalent hydrogens present on the same sp3 carbon is actually going to be having a coupling constant of about like 12 Hertz. Whereas if it's going to be present on sp2 carbon, then it's going to be very less, about 2 Hertz. And for the trans hydrogens, trans non-equivalent hydrogens, it's going to be 15 Hertz. And for the cis, it's going to be 10 Hertz. And for long-range coupling, it's going to be very, very tiny, which is about 1 Hertz. Okay, so using the coupling constant will help us to determine the neighboring protons and give an idea of about which protons are coupled with each other. Now let's see how the coupling constant can be useful in determining the cis and trans configuration in NMR spectrum. Here is 1-bromo-2-fluoroethene, which actually can exist in cis and trans configuration. When you look into this compound, there are two different types of protons. And here are the two different types of protons. Let me designate this as HA and HB. Okay, here is my HA proton and this is my HB proton. And similarly, these are the two protons I have, HA and HB. So on the whole, there are only two different types of protons in both of these compounds. When you look into the chemical shift, the HA is going to be downfield, is going to be upfield. So they're going to be here. If it's going to show a peak, then it's going to be in the upfield region with relative to the HB protons. And the same pattern is going to be expected for the cis as well, where the HB protons will be downfield and the HA protons will be relatively upfield. Then when you look in the integration, it's going to be, the two peaks are going to be in the ratio 1:1. And the splitting pattern, each of this peak is going to be existing as a doublet, because when you look into the A proton, it has one neighboring proton and therefore it's going to be split as n plus 1, which would be 1 plus 1, that would be a doublet. Again, the B proton will be split by the A proton as a doublet. So this peak right here will be split as doublet when you look into the splitting pattern. So which is going to look something like this. And the same thing is going to happen for this cis compound. Okay, remember, this is your hydrogen, and if you look into this, this is your neighboring carbon, and that carbon has one hydrogen, and therefore this is going to be split as a doublet as well. Both of these peaks is going to be split as a doublet. Okay, and this is our HA and this is HB. Okay, now how can we differentiate both of these compounds? Because we have exactly the same number of protons, they're going to show both of these protons going to both of these compounds going to experience the same type of chemical shifts in the two protons, and then they are going to be of the same intensity and they are going to be exactly providing the same splitting pattern. Okay, one way to distinguish the cis and trans configuration is to determine the coupling constant. So if I'm going to look into the distance between these two peaks, which is going to be called as JAB, okay, and then or JBA, whichever it is, for this trans compound, the JBA or JAB will be definitely going to be equivalent to or approximately going to be equivalent to 15 hertz. Whereas for the cis compound, it's going to be somewhere be equivalent to 10 hertz. Okay, so with this, we can definitely be able to identify the cis and the trans configuration in an NMR spectrum.